will say welcome to everyone, and we will take a few seconds to let people file orderly fashion into the room. And while we're doing that, I will mention slowly what we're doing here during this hour. This is a conversation on visualization and AI, actually in two kind of mirror forms, with my great friend, longtime friend, Chris Johnson. Chris is the Distinguished Professor of Computer Science at the University of Utah. He is the founding director, or was a former founding director of the SCI Institute, Scientific Computing Imaging Institute at the U of U, and he is also, I'm proud to say, on the advisory board for Pattern Computer. So welcome, Chris.
Thank you, Mark. Good to see everybody again. I see many familiar faces and names.
Yes, welcome back to FIRE.
Now, yes, it's been a little while. So I actually went back to my 2019 presentation to grab a slide or two to just kind of remind people, and it's actually integrated into what I'm going to talk about today. So if you've seen my presentations before, you know that I show lots of visualizations and talk about them, so that will be the same here as well, and then we'll hopefully have some fun questions. So So
Chris, before you start, I want to do a little housekeeping here.
Okay.
I remind the crowd, our audience, that at the end of your discussion today, we're going to have 10 minutes for audience Q&A. And if they have any questions during the time, they can post them into the chat box, and then we will call on the audience directly when that comes up. So I want to mention one more thing, which is that you have been at FIRE a lot. And traditionally, I believe we've always launched the top of the day on, it's usually Tuesday, with you at the front of the line. So my apologies for not getting you into that position, but I'm very happy to have you with us. And so please go ahead, and I'll try to only interrupt in the proper flow-like fashion.
All right. And it was great to be the hit-off batter for a number of years, but you can't always be the hit-off batter. So it's fine to let other people do that. Okay, so let me share my screen, and
there we go.
Let's see. I'm gonna just do some hiding of remote controls and things like that. Can see things. All right, can you see my screen okay?
Yes.
Great. Okay, so when Mark and I were talking about topics for this year, he was mentioning that there was going to be a significant AI theme in this year's FIRE, and it turned out that I was in the process of writing a book chapter on AI and visualization. So I thought, well, that could be fortuitous, and maybe it would make some sense to talk about that. So I'm going to talk about AI for visualization and visualization for AI. So it goes both ways, and I'll show you what I mean and give you some examples of that. I do want to just do a little background, tell you about the Scientific Computing and Imaging Institute, the acronym SCI, which we pronounce SCI. We're the SCI Institute, which works well in Utah. We actually have some pretty good snow this year for skiing. We could always use more, but it was a better skiing year this year. And the Institute is about 200 faculty, staff, and students from multiple departments around the University of Utah, and they specialize in scientific and information visualization, in biological, medical, and geophysical image analysis, and in biomedical and scientific computing. And we're actually expanding the Institute. We have 8 open faculty positions right now, and it's really great because we have an open faculty position in computational oncology. We have another one in bioinformatics. We have another one with the Museum of Natural History, and also one in urban ecology for biodiversity. So and they intersect with all of these visualization and imaging and modeling and simulation, data science, et cetera, that we do. So it's an exciting time right now for us. So one of my specialties is in visualization, in data visualization, and we work with a large number of application researchers in science and engineering and medicine, and that's expanding now into social sciences and finance and even the humanities, to find new abstractions and ways to turn that data into something our visual perception system can understand. So more than half of our brains are used for visual processing. We're very visual creatures. From a previous fire conference, I learned that whales' brains are 80% for sound. So they're not going to be probably a good user of our visualization tools, but humans are. And so if we can find ways in which to take those large, often complicated, often high dimensional data sets and find an abstraction and a mapping to something we understand visually, we have a better way, a good way to understand that data. And what you see in this image are some examples that we've worked on over the years. In the middle is a visualization of a simulation, largest simulation of a spiral galaxy forming. That was done by Elena Dongnia, who was at Harvard at the time she did that. And there was no visualization system that she could look at her simulations from. It was many terabytes of data. She found me, FedExed her disk to me, and we used this ray tracing system that we created, parallel ray tracing system, to be able to visualize her data. That one on the middle right is a simulation from Jacqueline Chin at Sandia National Labs. And she does the largest combustion simulations in the world on these big DOE supercomputers. And each one of her simulation time steps is 4 terabytes. And she does thousands of these. So she gets petabytes of data and wants to analyze and visualize those. And the one on the left, that's from Mariah Meyer, who's a previous fire speaker. And she does information visualization, and this was from comparative genomics of looking at chromosome mappings between humans and other mammalian species, looking at models of matching chromosomes. And so we work in lots of different ways to do that. Some motivation for why we might want to use machine learning as a way to help us with some of these visualizations. And then also motivation for why we think using visualization to better understand how machine learning works. Let's go with that. So this is a recent visualization of it's called the NASA Exajet dataset. It is enormous, and it's showing the flow past this jet here, and it's so large scale that the simulations have to use adaptive refinement of the meshing. So they can't just make the simulation grids all the same size. That would make our lives much easier as from the visualization graphics point of view, but for them, they just don't have enough degrees of freedom if they did that. And so they make places that have really high flow, like up by that front wheel, as you see there, where you have all these vortices peeling off of there. They have to make the grids very, very, very small. And then further away from that, they can make them large. So you have this hierarchical adaptive mesh. And that causes us challenges. So we actually created a ray tracing, parallel ray tracing system that could do this. And that one image is 1.3 billion cells. And we were able to create this system that was able to get 6 frames per second of visualizing that interactively. But it's getting bigger and bigger. Data sets are even bigger. And we can use machine learning and deep learning to create models and train models that allow us to basically do compression, creating these latent embeddings, and allow us to do the interaction at much higher rates. And I'll tell you some about that. This is another example of a very large scale data set. It's a Rickmeyer Meshkoff fluid simulation where you have a heavy fluid separated by a lighter fluid, and they take out the intermediate door, and then they mix, and you get this turbulent mixing. And again, this is in the hundreds of terabytes of data sets, and it's volume rendered. So we're looking at, instead of just the kind of the surface of the flow, we're actually looking at the entire volume. I want to play that again just so you see that thing in the upper right is called a transfer function. And that's what we're interacting with in order to change what you can see. So it's changing the transparency, you can change the colors, and that transfer function is kind of an art. So that's a one-dimensional transfer function, and volume rendering is a lot about solving the rendering equation. And the way you do it is that transfer function, you map the light model to different colors, and then opacity, which is 1 minus the transparency. And so we can use machine learning as a way to basically learn the rendering equation. And so allowing us not to have to solve the rendering equation, but we train a deep neural network to do that for us. And I'll give you an example of that. This is some more recent work where again, the large scale nature of the data sets that we continue to get just keeps getting bigger and bigger and bigger. And in order to see the detail, we need more pixels. And so this is the power wall we have at the SCI Institute, and it's 36 30-inch monitors all put together to give us 41 megapixels of resolution. And so, in terms of zooming in on these kind of super resolution images, we can now do that with this kind of technology. And we created this kind of easy to use cluster and made open source system so that anybody can go out and put a bunch of monitors together and then grab our software off of GitHub, and then be able to do this kind of visualization. And this is another place where, because of the super resolution at the data sets, if we want that interactivity, we really want to be able to train something to be able to have more, to do some of the compression and be able to do it more in an interactive way. This is my colleague Valerio Pascucci down there, and these are some of his amazing the work that he's been doing. Where he's on the upper left, we've got drones flying over industrial farms, automatically stitching together all of the images of the drones interactively, and being able to do analysis on that. What you saw on the upper right is an interactive VR experience of tracking neurons in the brain. And I think Mark has actually done this. He's had the headset on at the SCI Institute and track those neurons just like that. And one of the real challenges within VR is, for really high resolution, you don't have the frames per second in the current systems. And so you just don't want any lag to happen, or you get sick really quickly. So we've been doing streaming of those images. And again, we can use machine learning as part of the process to be able to do that. So that we can get interactive, very high resolution in a VR environment, which is what we all want. And the last example is some work I've done with one of my former students, Hanwei Shen, who's a professor at Ohio State University, and actually helped with some of the slides for this. And it's about flow visualization, fluid flow visualization. In this case, we're looking at these flows of very complicated three-dimensional flows, and we created this interactive lensing system to be able to go in and interactively look at these flows. And it's very sensitive and interactive, so you can just kind of twiddle each of these streamlines and look at them. And then this also has some applications in neurosurgery for diffusion tensor imaging, for pre-surgical planning, for tumor resection, which we're continuing to work on as well. But with the flow visualization, one of the real challenges that exists is, you notice this is static. Well, flows flow, they're time dependent. And there is no way right now to do interactive three-dimensional flow visualization for large-scale data sets. The only way we can do it is we record them frame by frame, and we play them back as a movie from one viewpoint. Well, that's not so great for wanting to interact and really explore your data sets. And so this is an example where, again, we can use machine learning to actually train a network to predict where the particles are going to flow. Now, I will show you that we just published a paper on this. Like, it hasn't actually come out yet, but it's been accepted for publication. I'll show you what that looks like. So the last FIRE, 2019, I guess, I gave a talk on uncertainty visualization. I asked the question of, when is the last time you've seen an error bar on a 3D visualization? And that was the premise of my whole talk. And we had done lots of work in this area. And for this talk, my question is, when is the last time you've seen an error bar on a machine learning or deep learning result? And the answer, unfortunately, is not so often. It's like you put the stuff in, you get the black box, you get something out, but it doesn't come with error bars and confidence intervals. Well, we need to do that. And so I will tell you about some efforts in that area. So as I mentioned at the beginning, when Mark and I talked about what I should talk about, this book that's by Alok Chowdhury and Jeffrey Fox and Tony Hay is in the process called AI for Science. And it's a huge undertaking. They've got lots of big name people writing chapters for this. And they asked me if I would write a chapter on AI and visualization. And I grabbed Hanwei Shen, who is a former student, long 25 years at Ohio State as a professor, and he is one of the world authorities, international authorities on using visualization for AI and vice versa. And he kindly shared some of his slides with me, so I wanted to make sure and acknowledge him. And it was really fun for me to create this, both the chapter and also this talk, because I also like to have just a little bit of history and find out what's going on in these talks. And so I must admit, I had no idea when the use of AI started in computer graphics and visualization. So I went back and looked, and it's further away than I thought. So it actually, the first paper that's acknowledged to be an AI for graphics and visualization is this one from 1986 by Jock McKinley. And it's on automating design of graphical presentations of relational information. I went and got the paper. You can find it actually on the Tableau website. And he has this model, this AI model for like reorienting bar charts and other graphical primitives in a way that is better than if you just did it from the program that you were using. And so for those of you who don't know, Jock McKinley he's really a pioneer in visualization, and especially in information visualization. And he is the first technical fellow at Tableau Software. So when Pat Hanrahan and others started Tableau, he was one of the first people they grabbed to hire, and he headed their information visualization design team, and now is a technical fellow, which I think means he can do what he wants now, whenever he wants. But he's won all kinds of awards and pioneer in graphics. Okay, so let's move ahead and kind of look at what's been going on in visualization and AI. This is from a recent survey called Applying Machine Learning Advances to Data Visualization, which they call ML for Viz. And this was the chart they had. It went up to 2020, and there's been loads of stuff in the last couple of years. But you'll see it really kind of started off in earnest around 2009 is what they think, kind of from modern machine learning and deep learning to visualization. And then you see this ramp of papers that just started more and more and more and more papers, and they continue to today. But what's interesting for this is that the blue is the visualization task that they were using AI for. So there's interaction and perception, there's data processing and communicating insight, presentation, etc. And then on the kind of orangish color is the kind of AI that they used for implementing for the visualization. And you'll see that it kind of just started off in the beginning, it was almost all classification. So it's all these convolutional neural networks, there's a little regression that's in there. But if you look at the right graph, you'll see that at some point, maybe around 2019 or so, that it really started to take advantage of more advanced AI systems and machine learning with semi-supervised and unsupervised and reinforcement learning and generative, some GAN networks and things like that. And that's really what we've seen. And so it might, I don't know if it's surprising to you, it's a little surprising to me, but I guess AI is just everywhere, and it's absolutely throughout the visualization community on both sides. And so let's talk a little bit about AI for Viz for AI. So we've got these black boxes of machine learning and deep neural networks, and everybody wants to know how they work. The inverse problem of solving that, what's in the black box and how that works is an unsolved problem at this point in time. So explainable AI is a hot topic, and Mark mentioned that there's going to be a reveal about pattern computer that will have something to say about explainable AI. On the visualization side, there's been a number of research, both papers and software systems just in the last couple of years where they're using visualization to visualize what's under the hood. So the model and computational graphs, the training data, the parameters of the models, the test data, the regression values, the hyperparameters, all of this stuff, and how do those embed into a deep neural network, and specifically in particular applications. And so let me share a few of these with you just to give you an idea. And I chose ones that are open source and available. So if you are doing some AI and you'd like to know more about what's underneath the hood, you can grab one of these and see if it might help for you. All right, so we've got deep learning models, we've got supervised, we've got unsupervised, we've got reinforcement learning as some examples of some of the deep learning models that are popular, and also ones in which there's been visualization systems created to look under the hood. So there's a visualization. There's visualization for AI. That's what AI looks like. You got this big black box. There's a bunch of neural networks in there on many different layers that are all hidden, and then something comes out without error bars and confidence intervals. All right. Okay, so what about some ways to look under the hood? So if we want to open the black box, for example, how can we do that? Well, there's a system which is called Ganviz. So these generative adversarial networks, which have become very popular and very useful. And I'll show you some examples of this and the other way around in a little bit. And so what this does is it evaluates the model performance of the two sub-networks for the GANs, and it provides evidence and interpretations of the model's performance and allows you to have comparative analysis underneath the hood. And so you're able to go in and actually dive in to what's being under the hood of the way these GAN deep neural networks work is basically you've got a set of real images that you're there, and then you've got your neural network generated networks images, and then you have a discriminator that tries to tell whether it's a real image or a fake image. And you play this min-max game of trying to minimize a functional that maximizes that you will end up getting the right answer, that these are real images. And I don't know if you can see it, but there's in the upper right-hand corner, there's the the red is the generated images, and the green line there are the real images, and you're seeing how that discrepancy is going down over time. And actually, if I blew that up, you would be able to see what the images look like as you went through time. And they can, with this tool, you can go in and you can dive in to that and all kinds of other things to evaluate your performance and really compare what's going on underneath the hood. The next one is called Dqm Viz. And these are for reinforcement learning applications where you've got these deep Q networks. And these became famous, I'll say, with using them to work in an unsupervised way with like games. And I think the most famous example is the Atari Breakout. So Atari Breakout was written many years ago by Nolan Bushnell. He's one of our Utah alumni who founded Atari. And he did Pong before that one, and then Atari Breakout, and so it's the one where you've got, if you haven't played it for a while, it's got a bunch of stuff up here, and there's like a paddle underneath and a ball that goes and knocks off stuff, and you're trying to break out of the system. Space Invaders was modeled a lot after that, where the Space Invaders would come out. Anyway, so they created these DQN networks, these reinforcement learning networks, to be able to learn how to better play the game. But it's all a blind training process. And they showed, though, that when they got it done, that it basically had superhuman capabilities. So it played the game better than any human can play. And they then used this to train a bunch of other games that could outdo any human in terms of performance. But what's frustrating about this is that you don't know how it happened. And so what this Dqm Viz does is actually exposes the details of the blind training process in multiple levels, and you're able to dive into the larger space of these different levels and do comprehensive analysis of what's going on under the hood. And this system was actually given to a bunch of machine learning people who did the programming for these different games. And they thought, there were lots of great quotes about how they really thought that they understood what was going on a lot more now that they use this tool than when they were trying to figure it out from first principles. Oops, wrong way. And another one is called Deep Vid. So this is called Deep Visual Interpretation and Diagnosis. And this is for large image classifiers. Machine learning has been extremely successful in image analysis. So that was one of its first applications, and it's still one of the strongest applications. But it's still not understood how it necessarily works. And so what Deep Vid does is it actually trains a small local model that's faithful to the overall deep neural network. And in a sense, it's kind of, it's training a piece of the network with a piece of the network, but it's a much simpler model. It's linear, and so it doesn't have all these nonlinear components in it, and it enables one to actually get a better grasp of what is going on in the more complicated model. And so this is a way to get at what that is going on in these deep learning models. And again, these are just three of many different techniques that are different systems that have been being developed out there of using visualization and analysis to figure out how this stuff works, and to use it to improve performance, to decrease amounts of training time, and really kind of look under the hood of how this might work. Okay, so let's turn it around and say, well, how might we use AI for Viz? And there's a bunch of ways. And as you saw in that graph, those tables that I showed you, they are being used in many different ways for embeddings, for latent representation, so for imaging features. Classification has been a big one early on, especially for data. Simulation surrogates are really coming up for these physically inspired neural networks, the PINs and other ways in which we can, instead of having to save the entire huge amount of simulation data sets, we'll do a simulation surrogate where we can utilize the training of that simulation surrogate of the simulation data to predict what the visualizations should look like. I'll show you an example of that. The super resolution for reconstruction, data dimensionality, data reduction, compression, that's a huge one because the data sets just get so much bigger and bigger. Rendering, so solving the rendering equation, and then optimal visual design layout for better perception is another big one. Graph layout is a really hot topic right now in machine learning for visualization. All right, so let me show you some examples of this. So this is a volume rendering system that we created called ImageViz 3D. It's open source, you can grab it. And in that molecule up there, what you'll see is that's that transfer function. We're playing with the transfer function, and every time we move that, something the view changes. We're doing one on the bottom with the hand as well. And there's a two-dimensional transfer function now, and you get more specificity, but it's more complicated to figure out how to do that. And so Josh Vine, who's a professor of computer science at the University of Arizona, had an idea of, well, what if we replaced the rendering equation with a deep learning neural network? And so it learned the rendering equation. So he created a generative model for volume rendering. And the idea was that what he needed was to look at all these different viewpoints. So on the left there, that's an eye, that's a viewpoint of looking. So we need to look at something. And then the thing next to it is the transfer function. So that's the opacity and the color map that we're going to have. And then on the right is the generated volume rendering image that we're creating. And so what he did was he created a generative adversarial network, a GAN, to generate all of these different images that were based on different viewpoints and different transfer functions. And then he had a discriminator that would decide, well, is that generated image real or is it a fake? Okay. Oops. And so there are hundreds of thousands of images that had to be created in an offline way. It took more than 20 hours of training to do this one data set. And so wanted to be able to see if this was a possibility of then creating basically a map of images. So like a design gallery in a sense where the system, the GAN model, the deep neural network had solved the rendering equation, and you could just then see what the results would look like if you were to choose a particular transfer function and viewpoint without ever doing any of the solving of the rendering equation for you. So just to give you a sense of how good this is, you'll see the left, and then there's a right next to it. That's the ground truth volume rendering on the left, and then there's the synthesized. So we've got some bones. On the upper right are some fluid flow, really complicated fluid flow. In the bottom left, it's an engine block. It's a CT of an engine block. It's a standard one. And then there's the NIH visible male is in the bottom, the bottom right. And actually it looks pretty good. There are a few places where, for example, it just didn't quite get this edge, and there's a little bit in the shading that you can see. And then in the visible male, again, on the edge, there's something going on with the mouth there. So these were the original images. Then they went back and what it has to do with, there's a sensitivity issue. And so they retrained this to get even better images that you basically can't tell the things apart. So this is very interesting in that we've now solved this fairly complicated mathematical equation called the rendering equation by using a deep neural network. And now we don't have to have somebody spend time twiddling with a transfer function. We'll just see what all the options are and choose the one that we want in terms of the viewpoint and what we're going to see inside. So Josh also created another paper, a more recent paper, where they used this same type of technique to do compression and volume rendering. And so now because the data sets are just getting so big, if we can find ways to basically get better compressions, then that's a huge win. And there have been compression algorithms have been a mainstay for research for many, many years, and continue to be so. And so this is basically training a deep neural network to do the compression for you in the case of volume rendering. And just to give you a sense of how good this thing is, the original image on the left is a volume render of 512 megabytes in terms of the image that you have there. And that one that's on the right is 0.757 megabytes. So that's 676 to 1 compression ratio. And there is, at the edges cause problems for these things. It's on the boundaries. It's a tough thing to get, but otherwise, boy, it's pretty good, and it outdoes the more mainstay compression algorithms by quite a bit. So this is a hot topic because we want to be able to use this, and this provides interaction for us.
Chris,
all right. Yeah.
Is the problem with the edges that the system is it's looking at the change pixel to pixel, and therefore when you get to an edge, it doesn't have any more to work with?
Yeah, it's an information issue, in that you don't have as much information as you've got on the surface or interior spaces, and so people are trying to figure out valid ways to do that. Sometimes they do padding, sometimes there are other ways that they can try to get at that, but I'll show you in another one that's their endpoint issues and edge issues are still a challenge for getting these things right.
The obvious way to fix it is just do what you already did, get a kitchen knife out and just cut the last inch off.
Yeah.
You're in good shape.
That's right. Actually, people do that.
I bet they do.
So this is another one, and this is one of Hanwei's, Shen's also. It's a collaboration with Argonne National Laboratory, so Ohio State and Argonne National Laboratory, and it's called InsituNet. And this gets at the, like that Exojet NASA data set that I was showing you, or Jacqueline Chen's combustion data sets. On these biggest exascale data sets, they don't have the capability to save the data anymore from these. It's just too big. And so the old way of you do your humongous simulation, you write everything out to disk, and then you come in with your visualization tools and you analyze and visualize that. Not happening in the future. And so what we need is they got to figure out, these application researchers, what they get to save a little bit of the data, a small portion, and they fight screaming, I want all my data forever, and so I can go back and look at it. So it's not going to happen. So they have to choose, but they also, one way to get at both to choose and to see what's going on is to be able to do the visualization at the same time the simulation is running. And so that's called in situ visualization. And the many challenges of that, but one of it is the data set size. And so what this does is this is a surrogate model, and where you can do parameter space exploration. This is for ensemble simulations like large scale climate simulations or cosmology simulations. And they train this end-to-end mapping from the simulation. And you're then able to go in and interactively explore synthesized visualization images from different simulation parameter under different visualization settings without redoing any of the simulations. So this is what these application scientists want, because this is really a lot more like they've done it, dumped it out the data, and they can then go back in and look. Here we're using deep neural networks in order to do basically surrogate simulations and to do their parameter explorations. And I'll show you, I have a little video of this. So this one, first I have just to show you.
I should mention that we have about 5 minutes more together. And then the MC is going to interrupt us rudely or
Great.
nice and do Q&A.
All right, all right, I'll just go through. So this is another type of GANs that you see, and let's see, it's going to do both at the same time. Anyway, you got a cosmological simulation on the left, you have an ocean simulation on the right, and what you're seeing is that they're doing parameter exploration of sensitivity to parameters, and then on the left and on the right, they're actually looking at like different ISO surfaces of data sets and also doing sensitivity analysis. And the idea is that that is all being able to be done with a simulation surrogate that doesn't exist in real life. I mean, it's the neural network that's trained from viewing the simulations, but this allows them to be able to do this in situ interactive visualization and sensitivity parameters. Okay, one last thing, which is one of my research. This is the flow visualization that we've just finished. That hasn't been. It's not published, but it's been accepted yet. We're using these, and this is the idea here was that the time-dependent flow problems for large scale, you can't actually visualize them interactivity. You got to play them back as a movie because the data sets are just too large and you can't get in and do the analysis and visualization at the same time. So we created a deep neural network that does that, and we have these seeding that we seed the sets of particles in the flow so we can watch where the flows get, and we train these things, and this is what the neural network looks like. It's a multi-layered perceptron with a bunch of fully connected layers, and then it has the rectified linear unit in there that helps us with the activation function for the output, and helps us with some gradient calculations that are there. All right, just quickly. So we had a couple of different data sets. It's called the double gyre data set. And basically it's one of the test data sets that fluid folks use, where it has these two rotating gyres that go and interact. And so it's a time dependent data set. And then the other one is called the ABC data set. And again, it's a three-dimensional time dependent data set. And so just quickly, what we're looking at is some of our initial studies of the double gyre that we generated, and then we looked at the number of seeds, and we also looked at the size of the intervals. And what you're seeing there are some examples of whether we did long or short intervals in the seeds. And the blue that you see and then the red, those are the simulations from the neural network. And what you can't see is the ground truth because it's right underneath those. So it's kind of amazing. You start the seeds where those red dots are, and then it predicts, the neural network predicts where the particle will go in the flow. And what this allows us to do is greatly compress these enormous data sets down into like 10.5 megabyte data sets, in which we can then do this kind of flow evaluation for these complicated three-dimensional flows. You'll see that there's some differences and it's not quite perfect yet, but boy, it's pretty good. And that's my almost second to last slide of this is the ABC data set of where we have the ground truth on the left, so a complicated three-dimensional flow, and then what our deep neural network model predicted. And they're basically identical. It just kind of surprised us because this is really complicated three-dimensional flow, and it's like, wow, that's kind of predicting the physics pretty well of what's going on there. And so we're continuing to work on that. And then what I'll skip this stuff, close with is, well, what about the error bars and the confidence intervals? And that is now actively being researched. So there are some very recent papers on uncertainty quantification for machine learning and deep neural networks. And then this is a new visualization tool, it's called Classy, that is looking at evaluation of the classification performance and other applications of machine learning. And so putting the error bars on and the confidence intervals on the different algorithms that people are using for the deep learning. So I think that's a very active and needed part of this whole thing. And with that, I'll say thanks. So thanks for inviting me to fire again.
So I know that it's probably Barrett, it might be Evan, about to jump in. So it seems to me that you are right on the edge, if not over the edge, of unifying physical law or nature or whatever, with the, I don't want to say simulations, but with the networks.
Yeah, it's not just us. I mean, there's a whole world out there of these physically based neural networks, physically inspired neural networks, where, in the beginning with like the image analysis, I'll say that a lot of the imaging analysis and classifiers, automatic segmentation things, they just took the data sets, the images, and they just learned the data sets, and they didn't have anything in terms of the mathematics or the physics of what was going on. And now people are saying, well, there's some pretty good physics that are in there, and that these neural networks should obey when they're trying to do these classifications. And so they're merging the math and the physics with the machine learning, and it's becoming very powerful.
So are you learning new physics by doing this?
I would say I'm not, but I would say people like George Karniadakis, who's at Brown University, is one of the very much the leaders in this field, and they are starting to be predictive with some of their physically inspired neural networks. So if you put in Google Pins and Karniadakis, it's spelled just like it sounds, or Brown University, you're going to see these huge numbers of papers. This guy has this huge lab. I actually just moved to Johns Hopkins. Johns Hopkins just bought him from Brown, but so you might put in JHU for his name now. But he has spawned really this revolution in physics-based neural networks, and there are many other people are doing this in different areas as well, in physics and material science. And yeah, we're definitely going to see the merging of physics and neural networks. We are seeing them merge.
Gary, that makes it all worthwhile. Okay, so who's our MC right now?
We have a lot of questions, Chris, which is a good sign. It means that people are nerding out about what you're talking about. So I'm going to turn first to Eric Jansen. Eric, are you available to unmute?
Yeah, I'm just curious, as we explore the black box nature of these things, and Mark, I don't know what your reveal is later today.
Tomorrow.
Are there any hints, visualization tricks to tell us what's going on in the black box problem so that we can actually learn faster to learn how it's learning?
Yeah, there are. And, yes, the answer is yes. And I was going to just see if I can pull up.
I was hoping you'd say yes.
Yeah, the answer is yes. And
I actually knew you were going to say yes, but I want to hear the details of yes.
Yeah, I'll point you to the paper, but let me just. So the DQN paper, Viz paper. So they actually worked a lot with machine learning experts who used it, and then they did user studies, and so they got a lot of feedback in terms of the extremely helpful to have actionable insight into the model evolution. It has great potential to comprehend and improve deep learning models, could explore, observe, and extract meaningful patterns, ponder how the agent developed its playing strategies in the game, like Breakthrough. Let's see. Visualization had significantly improved my understanding about random actions, and the pattern lengths were actually turned out to be non-random in some cases. Anyway, so there's a whole list of how these machine learning people used it when they're evaluating their systems, like for the automatic game playing. And I will let's see. I'll put. Are you going to put
You can attach it. You can actually attach it to the session if you'd like. If there's like a document or something, you can attach
Okay,
it to the
I'll do that. I'll
session
put a-
after it's over, and that way people
Yeah.
can go back and look at it.
Great. I'll put a set of references where like links to papers and GitHub repositories.
That would be awesome. So
Thank
the
you.
next
Eric, it's-
question.
The XAI reveal is not today, it's tomorrow. Eric.
That's fine. I'll be there. Thank you.
The next question is from Bobbin. Bobbin, are you ready to ask?
I'm not sure if this even makes sense, but I've been working with systems of systems and how they form their holographic. And I was wondering if there are any visualizations that would look at a complex system of systems holographically. Zoom in contextually or abstract out and pan across.
And I'll just note before you answer that Brad, we're gonna go to your question next. So be ready to unmute.
And I don't know, I haven't seen anything specifically on that, but if you pop me an email with a pointer, I can certainly take a look and then follow up with you on if I find any leads or at least ideas that I have. Certainly the system, the system and system stuff. We have done holographic imaging as well. I haven't seen it all put together like that though, but it'd be interesting to find out more.
Awesome, thank you. I'll do that.
All right, Brad.
Delighted to see you again, Chris. So you talked a little bit about the compression
Yeah.
using AI. Can you talk a little bit about the compute requirements and the time requirements for that compression? And then also, you're limiting the models for much of what you're doing for the domains of where the models are being trained. You talked at the beginning of the talk about error bars, if you will, and confidence intervals. Do you have any insight into what can be done to predict where the model is likely not to stray far from reality?
All right, so let me answer the first question first. So like the compression, the work on the compression was done on, it was 16 hours to train on a NVIDIA GTX 1080. So not too bad in these things. The fluid dynamics ones that we were looking at as the data sets got larger and larger, they were multiple days on NVIDIA RTX systems that had 4 to 8 RTX GPUs in them. So not something you have usually on your desktop, and probably everywhere in between. I was saying, let's see, for the in situ net, for example, it was 20 hours using an NVIDIA DGX1 machine that had 8 V100s. So again, pretty hefty compute to get some of this stuff. And that, I didn't have time to talk about the return on investment for some of this stuff. That's a lot of hours and a lot of energy that's being done. And so you'd really want to be able to utilize this for multiple applications, or an application you were using over and over again, and not just as a one-off. Your question, what was the second part of your question?
About the bounds of the visualization.
Yeah. So I have not seen anything that's, I'll say, at least interactive. There's a group at Oxford that is doing some deep Bayesian learning algorithms, and they have some really great stuff on uncertainty quantification using these Bayesian models. And by the way, Bayesian models are compute intensive like you don't know. And they have been able to put error bars and confidence intervals on a lot of the systems that they're looking at. George Karnidakis has just a paper on arXiv that was just out on uncertainty quantification for machine learning. It's like an 80-page paper. I haven't made it through yet, but where he's really taken the math at it and trying to put those error bars on different machine learning algorithms. I'll try to remember to put those references in whatever I have at the end.
Thank you.
Thanks, Chris. So the next question is from Kon Sabalchikov. Kon, are you ready?
Hi, Chris.
Hi.
Brad asked the essence of my question, which was about limitations on visualization, whether it's computer processing power, whether it's algorithms or something else. But I want to really ask, would a chip like True North be able to speed up things where you have parallel processing of visualizations?
Yeah, so parallelism is huge. We're using it wherever we possibly can, and a lot of visualization, because we work a lot in screen space, where we can partition stuff up into nice little bits and just parts of the screen and send those off to different GPUs, and we can make these things massively parallel. So the more parallelism that we can have access to, the better. And so yes, that it's amazing the amount of computing that we're using for training these models. It's like every CPU and GPU people can get their hands on are being used to train this stuff. So that's why you can't get GPUs anymore. NVIDIA's, they're just like sold out because everybody wants to buy them to train their networks.
Do the lights dim in Salt Lake when you turn the switch on?
Yeah, basically.
All right, final question comes from Shalev. Shalev, are you ready to ask?
Yeah, and by the way, Mark, the lights dim in my room when I train my networks, actually. They flicker, seriously, no joke.
That's good. You're on your way.
Yeah. My apologies if you said this, but I had a question about the Dqm visualization.
Yeah.
Is it more on, because we had a question, I think, from Eric about the black box nature, and you mentioned this Dqm visualization, right, to see how the training progresses over time, how it's changing, how it's evolving. Was that visualization and kind of analysis more on the output and behavior of the RL agent, or was it, which is I think much harder, actually taking into account the specific weights of the network and extracting some information from there, which I think
it's definitely looking at, so there's this like 4-stage thing where they predict, act, observe, and learn. And they're looking at the agent's experiences, they're looking at network parameters, they're looking at like hyperparameters, other things that are there, they're looking at summary statistics. So they actually are looking at all different parts of the view, in addition to how well the network is responding overall to what's going on. And it's set up so that you like look at stuff every so many steps, so you can break it down and just look at where you're at in terms of the training and pull stuff off, and then see how well things are trained at that point, and see what's going on at that point, and then do more and do more. Let's see, actually looking at the paper, I've got it open on my laptop sitting next to.
In terms of, in general, work that's been extracting information from the weights of a neural net while it's training in order to gain insight, yeah. What is your current feel of the current state of that in the field, in the research field? Yeah,
I think it's still evolving, but it's, I think what people are at the point now is they're kind of looking for patterns. It's the pattern, and looking for patterns in that, and then finding patterns, and then trying to understand and dig down a little deeper on how those patterns were generated. But there's in this DQN, for example, they use like principal component analysis in order to project stuff out, and in order to find what those weights are. What are they seeing the most? What's the next most? What's the third most? And kind of using some of that analysis to dig down into some of the patterns that they're seeing. They also use saliency maps and other visualizations. So there's like, I don't know how many different ways that they look at this, but there's a bunch of different ways in terms of trying to get at what's underneath. I'm not an expert in DQ, it's not my system, so I didn't invent it. I just know a little bit about it. So what I recommend is you go grab it and try it out.
And he probably will do that, actually.
It's good. And it's one of Hanwei Shen's systems, who I mentioned, my former student and co-author of this paper, and so he He has a lot of great stuff on it. I'll send you off the paper as well.
Awesome.
Looking for patterns makes sense.
I know, I was gonna say, so we are out of time. Chris, thank you so much for
Sure.
joining us and sharing
thank you.
all of your incredible research and innovations with us. It's
Great to
it's
see everybody.
an honor to be here.
Great as always.
All right, I'll follow up with some references and links. All
Cool.
Thank
See
you
you
so
soon.
much.
right, good night, bye-bye.
Bye.
Thank you.